Welcome to Brain Vision.
Okay, so for this question, our first step is to determine the rate of heat transfer in the air. Okay, so first let's set out the energy balance equation here, which is E dot in equal to E dot out. If we expand it, we have Q dot plus M1 dot times H1 is equal to M1 dot times H2. Q dot in here is the rate of heat transfer in the air, and M1 dot here is the mass flow rate for the air, and H1 is the initial enthalpy for the air, and H2 is the final enthalpy for the air. If we do some arrangement here, we have Q dot is equal to M1 dot times H2 minus H1. So we know M dot 1 here can be equal to rho 1 times V1 dot. Rho 1 is the density of air at the inlet. V1 dot is the inlet volume flow rate for the air. So we know that rho 1 can be also expressed as P1 over RT1. So eventually we have M1 dot is equal to P1 times V1 dot over RT1. And we know H2 minus H1 can be expressed as Cp times T2 minus T1. Cp is the specific heat for the air, and T2 is the final temperature, T1 is the initial temperature. So now we have Q dot is equal to P1 times V1 dot over RT1 times Cp times T2 minus T1. So we know the inlet pressure for the air is 100 kilopascal, and the inlet volume flow rate is 600 meter cube per minute. If we convert it to meter cube per second, it's 10 meter cube per second. And the R is the gas constant of air, which is 0.287 kilojoule per kilogram times Kelvin. And we know the initial temperature for the air is 27 degrees Celsius. If we convert it to Kelvin, it's 300 Kelvin. And the specific heat for the air is 1.005 kilojoule per kilogram times degree Celsius. And the final temperature for the air is 60 degrees Celsius. So now let's plug into the equation. Eventually, we'll have the rate of heat transfer in the air is 385.192 kilowatts. Since the value is positive, that means the air is gaining the heat. Okay, so if the air is gaining heat, that means the refrigerant 134A must lose the heat, since all this is based on the energy conservation law. Okay, so we have Q dot R, which is the rate of heat transfer in the refrigerant 134A, is equal to negative Q dot, which is equal to negative 385.192 kilowatts. So we know Q dot R can be equal to MR dot times HR2 minus HR1. So MR dot here is the mass flow rate of the refrigerants we are looking for to determine. HR2 here is the final enthalpy for the refrigerants 134A, and the HR1 is the initial enthalpy for the refrigerants 134A. So if we do some arrangement here, we have MR dot is equal to QR dot over HR2 minus HR1. So we know QR dot is negative 385.192 kilowatts. So for the initial enthalpy of the refrigerants, we need to use the superheated refrigerant 134A table, which is table A, let me see. Table A13, okay? So at 1 megapascal, 90 degrees Celsius, you have the corresponding enthalpy for the refrigerant 134A is 324.66 kilojoule per kilogram. And then for the final enthalpy of the refrigerant, in this case, we need to use the saturated refrigerants 134A temperature table, which is table A11, to find out the corresponding enthalpy. So at 1 megapascal, 30 degrees Celsius, we'll have the final enthalpy is equal to 93.58 kilojoule per kilogram. So now we can plug in back to the equation to determine the mass flow rate of the refrigerants, which is equal to negative 385.192 kilowatts over 93.58 kilojoule per kilogram minus 324.66 kilojoule per kilogram. And this will give us the mass flow rate for the refrigerants 134A is about 1.67 kilogram per second. If we convert it to kilogram per minute, is 1.67 kilogram over 1/60 minutes, since we know 1 second is 1/60 minutes, and this will give us the mass flow rate is about 100 kilogram per minute. And this is the answer for this question.